Good morning, it's Max Isaac with Hitachi Consulting for the International Data Engineering and Science Organization with some remarks on feature engineering. These remarks will be the content of the Ideas Webcast on Saturday the 2nd of March, and today is Sunday the 17th of February, just with a pre-recording for the benefit of our Hitachi Consulting Quant Clinic forum that we have for our data scientists inside of our Insight and Analytics group at Hitachi Consulting. I'm very pleased to be involved with Ideas. We had a fantastic conference last June of 2018 at the University of Chicago on the topic of artificial intelligence and blockchain. Lots of good ideas exchanged, and I'm really pleased to be addressing the webcast and to be asked to do so. So today we'll introduce a small data set and review the idea of expanding a function into a power series. That's the topic of your undergraduate calculus sequence, your high school calculus sequence, and a word about the radial kernel and how that helps us in machine learning. And we'll just use those as motivations for some of our feature engineering of higher order features. We'll just keep that in the back of our mind as we do our work. We'll illustrate the idea here with a nonlinear decision boundary and some mapping into hyperspace, and then I'll review a simple polynomial kernel in R. The polynomial kernel maybe being a little easier this morning than the radial kernel to get our minds around, certainly my own mind anyway. And perform some baseline machine learning. We'll find that leaves something to be desired, so we'll do our work and engineer some features, and about that time we'll realize we really need to think about the data generating function and the physics of the problem and use those physics to guide us, not just in a machine learning study, but a data science study. And then we'll compare and contrast that with a machine learning result. And then we've got some news you can use. It turns out these topics are in the news cycle today, this morning, as we speak, and I think will continue to be discussed given the critical mass that is in the academic community around how machine learning is used in science. Well, here's our data set. It is a GBB, a good, better, best classification with height versus weight. With in the z-axis is a physician's categorization of health with one of 6 categories: underweight, normal, pre-obese, and then 3 classes of obesity. And so maybe if we can predict on that pre-obese, we can assist a physician, for example, with some counseling the patient on some behavioral modification or perhaps treatment. That's our goal. Well, just a word about the idea of expanding a function in a power series and how it relates to machine learning and especially feature engineering. If you remember from your calculus sequence, it's possible to expand a function around a point, and the prefactor there is, remember, the subsequent derivatives of the function evaluated at that point with an appropriate denominator. Very often that's a factorial or a function of a factorial. And remember that that was Taylor's work. And remember, these functions converge subject to limits. Not every function is defined everywhere around that expansion. It may have a radius of convergence. But remember the exponential function, especially with the work of Maclaurin there, who considered things around the origin where a was 0. Remember, the exponential function expands in all power of x, and it converges for all x, which is a really cool property of the exponential function. And that was used, and I could go on and on with that, but let's just leave that as an idea in our mind, that we can expand the exponential function in all powers of x as a motivator for feature engineering. And this has actually been put to amazingly successful use by Vapnik and his collaborators in the support vector machines, and then of course all sorts of applications after Vapnik published his works. But the radial basis kernel function for the so-called kernel trick of support vector machines and other algorithms, it starts with this exponential expression, and you might recognize that as something that sure looks a lot like a Gaussian, doesn't it? It's got a Euclidean metric there in the top with some kind of support vector, the difference between your position and some support vector, in units of the variance. And so we've got a lot going on here. It's something that looks like a Gaussian, and it is of course therefore expressed as an exponential, and we know that we can expand an exponential in higher powers of the x vector. So a lot going on there. And again, I'm going to leave that alone. We could wrap a 2-semester graduate sequence around that topic, but let's don't do that now. Let's just keep these thoughts in mind, that this so-called the so-called kernel trick is integral to feature engineering exactly because it lifts us into a higher dimensional space from our x to our powers of x. And so a little bit of explanation is due, I think. Here's a linear decision boundary that I think we could all draw between the blue guys and the red guys. And now it's possible that I have some kind of nonlinear boundary. And let me get my pointer here. Bear with me. I have some kind of crazy nonlinear boundary here in this 2 space. And the reason that's a problem is that it's a geometric fact that if you have triangles of one species in that space with the other species encroaching on that triangle, here I have a picture of it. There it is. Then indeed you cannot draw a linear decision boundary through that triangle to separate those 2 species. And I'm not prepared to prove that this morning, but maybe you've seen that go by in your geometry work. But if we can apply this kernel trick, then I can lift this into a higher dimensional space. Now, looking down on these dots, I get right back to where I started, so that doesn't help me. But if I look in these other dimensions of this hyperspace, in this case these 2 other dimensions, I can draw this hyperplane through and get a good discriminator and a good separator and some good decision discrimination capability on this data set. That is the raison d'etre of the kernel trick. Let's go through a polynomial kernel. Let me walk you through it. This is our code, if you can read it. So we got u here in 2 space is the vector 1, 2, and v is the vector 3, 4. And we're going to define this Hadamard function. You might remember that, the Hadamard product from your linear algebra. It's a little different than a matrix or a vector multiply. What it does is it takes the product of the 2 vectors and the first vector element as well as the second vector element and returns that as a 2 vector. So the Hadamard product returns an algebraic 2 vector here. And the self product we'll define as just simply the cross terms. And so we can define this kernel here as a function. It takes 2 vectors and it returns the Hadamard of the 2 vectors together and sums that value. And then it takes the self-Hadamard of the first vector and times the Hadamard of the second vector, the self-Hadamard of the second vector, and sums that value. And then it takes the product of the 2 self-products, first of the s vector and then of the t vector, and adds that to the sum. And it returns this number. So it's one metric on this 2 space that's a digest, a kernel digest, on these 2 vectors u and v in this 2 space. For those 2 vectors 1, 2, and 3, 4, it is the value 108. If we define a second function phi, known as the kernel certificate, then it takes as an argument a vector, and it regurgitates the vector to you. It takes a 2 vector here and regurgitates a 5 vector back at you. So it takes the v vector and returns it. And then as the other vector elements, it takes the first vector element of v squared, the second vector element of v squared, and the cross term. So we get 1, 2, 3, 4, 5 elements back at us. So we send 2 and we get 5 back. So let's calculate the phi kernel certificate on the u vector, which remember is 1, 2. So I've got 1, 2 right back at me. We got the square of 1, the square of 2 is 4, and 1 times 2 is 2. So I have the 5 vector 1, 2, 1, 4, 2. That is the kernel certificate of the u vector in 5 space. Now let's calculate the phi of the v vector. The v vector was 3, 4, so I've got 3, 4 regurgitated right back at me. I've got the square of 3 is 9, the square of 4 is 16, and the cross term is 12. So it sends back to me as the kernel certificate of the 3, 4 vector in 2 space. It sends the 5 vector 3, 4, 9, 16, 12. Well, so what? Well, here's my kernel that I calculated in 2 space. Remember, the digest is 108. We just calculated the kernel certificate of u. It was 1, 2, 1, 4, 2. And we calculated the kernel certificate of v, which was 3, 4, 9, 16, 12. Now, the interesting thing is if I take a vector multiply of that, so not a Hadamard product, but a vector multiply, of the certificate of u times the certificate of v, it returns this digest of 108. So this thing, if I have a properly structured kernel with a validating kernel certificate, I can recalculate this vector metric of 108 in either my original 2 space or my hyperdimensional 5 space as I work with these vectors. That's the power of a kernel. In fact, a kernel is defined only for something that has a valid kernel certificate accompanying it. And there's only so many of those. Well, maybe we'll leave that for another course. But there are only so many of them that have really been have found common usage in machine learning. So what we've done is we have this crazy data set here in 2-space, and there's no linear decision boundary. I use my mouse, sorry for the artwork, but I've got this decision boundary here to separate the two species. And remember, what we're doing is lifting that into a higher dimensional space, which here has been depicted as a 2-space, but this is, remember, a hyperplane in our example, 5-space. Now remember, Vapnik and his collaborators can actually give you an assurance on this gap. That's one of the powers of the support vector machine classifier. We'll leave that alone for now, but remember, it does come along for the ride as part of the work around the radial kernel function of support vector machine, and the transition is the so-called kernel trick. In this case, I illustrated a polynomial kernel, but in wider practice, perhaps the radial kernel, exactly because it gives you a power series expansion, an infinite series expansion for the exponential. So let's do some work here. We're after this pre-obese categorization. So we've got health and height and weight. That's what the data set has. So let's do our work here. So I've got my analytic data set. By the way, I didn't center and scale these numbers. It wasn't important for me to make my point, but consequently, the statistical advice that comes back at us from our regressions is going to shock the conscience. So I'll do that without apology, but we should center and scale our data, of course. But I didn't want to get, maybe it's a little easier to see inches and pounds than it is to see z values of those. So I kind of left it alone, but sorry about that. So we're going to mark up our analytic data set. I'm going to pull off y here for my multivariate regression. And if it's a pre-obese category here, I'm going to mark him with a 1. That's my class. And then otherwise a 0. So I should have 1,860 of those. And if I table my y value, it looks like in 2 lines of R code, I managed not to mess it up. There they are right there. Everything else is not pre-obese. Now remember, because of that, our baseline our baseline value is 81.4%. That's our baseline. So until we've got a better predictor than 81.4%, we haven't done anything. Let's do our work here. Here's our multivariate regression. Again, the prefactors shock the conscience. The p-value looks very handsome, doesn't it? But be careful about that. Don't p-hack this. That's not the way we use it. We have no hypothesis against which we're testing. We're just simply doing a multivariate regression on some factors. So we can't really make use of this p-value here, although it would be nice if our prediction is within a certain standard error so that we can publish our results. But we're not there yet or anywhere near there yet. So let's keep going. So the problem is this actually does not work. This is a very unsatisfying result. This is a plot of accuracy, a true positive rate, and true negative rate as a function of the thresholds. And you can see my threshold to make this work at all has got to be kind of down here in the 0.2 range. That's not the way a good analytic data set should behave. I mean, that threshold certainly can be manipulated, of course, but you'd like to see it in the 0th order be around the 0.5 range. But here it's nowhere close. And my true positives just fall off, and my true negatives go up to 1. In other words, and the accuracy goes to about what? Well, 81.4%. In other words, this thing just gave up. It cannot classify a true positive. Now, that's not a complete loss, especially, for example, in high-speed fraud detection. Some of the thinking, especially with autoencoder technology, is that you can simply classify the non-class and then use even traditional business rules or other machine learning techniques to go after the class. But this is not that, and so basically this failed. So we got to go back to the starting board here. Now, if I calculate the area under the curve for height and weight, which I would have done in anticipation of this calculation, I would have done it as part of my feature engineering, you would find that the area under the curve for height alone is 81% and for weight is 76%. So we haven't done anything to help ourselves with this calculation. So we have to calculate some more features. So here's where we're going to start using some power functions on our features. So I'm going to take the square of each. I'm going to take the cross term, height times weight. Those are all second order features. I'm going to take the ratio of one to the other for both height and weight, and I'm going to redo my work here. So let's set up our work. Here's my second order features. I've got my markup in my pre-obesity here, my good, better, best. If it's a pre-obese, I'm going to mark it 1. I've got 1, 2, 3, 4, 5, 6, 7-dimensional hyperspace. I'm going to try to draw a 6-dimensional boundary here. Let's see how I do. Again, don't p-hack this thing, and the coefficients, because I didn't center and scale the data, are kind of wonky, but don't worry about that. But this thing actually did a little better for us. Notice that my threshold around 0.5 here is behaving better. It looks a little choppy, but Professor Edward Tufte actually would hold me in contempt. You can see that he says don't ever present data where you don't have the origin on the axis, and indeed I don't. So even though it looks choppy, we're bouncing around 3 nines here. So if I had the origin in there, that would look a lot smoother. Nevertheless, it's unsatisfying, and in fact, you can see my true positives are falling off again. The accuracy, although it can be very good at times, is having trouble kind of getting there, and it's kind of choppy and unstable, and that's not the kind of decision surface you would like to see. So we need to do some science, and so here's what we're going to do. Oh, and by the way, if you calculate the area under the curve, there is a hint. Nothing helped us very much except these ratios. There's some signal in those ratios. That's interesting, isn't it? So the square of height did no better than height itself. The square of weight did no better than weight itself. The cross term actually did worse. But the ratios seem to be talking to us somehow. So Mother Nature's talking to us. But let's do some science. We really haven't done any science here. And we really need to figure out the data generating function for this thing. Let's stop for a moment with the machine learning razzmatazz, and let's actually do some good old-fashioned science. So remember, we're kind of cylinders, as human beings, don't you think? That could be a model. Now, you'd probably tell me your height. I don't know why you wouldn't, but very, very few of us would like to disclose our width. That's not a very flattering number, at least in my case. So I can get the height, but I'm probably not going to get the width, or I could do some kind of blind polling or something, but I'm probably not going to get it. But I don't need it to figure out the decision heuristics of the data generating function for this problem. The volume of this cylinder, you'll remember from your certainly junior high school days or earlier, is pi r squared h, but that r you can see is some kind of an effective r. We're not all the same, so it has a probability distribution to it. Remember, this is very important. The answer to any decision under uncertainty is not a number. It's a shape. It's the shape of the probability density function of that random variable. And in fact, the volume of us is a function of a random variable. Well, what function? Well, I don't know. I picked this one out of a clip art library, but we would have to undertake a scientific study to establish that probability distribution. Now, the weight, therefore, is that volume times some effective density. Some of us are muscular and some of us are pleasingly squishy, and that's what makes the world go round, of course. But there I go again. I've got yet another function of a random variable. So I've got two of these things. I don't know, maybe the distribution of the density, the hard bodies and the soft bodies, maybe it looks kind of like this. I don't know. So this weight, I know the arithmetic. That I've known that since elementary school, haven't you? But unfortunately, and that's an elementary school topic, but this weight is a function so far of two random variables, and that is most decidedly not an elementary school topic. That is a graduate school topic. Well, I'm just fixated on this radius, but the fact is I can't get it. No one's going to tell me. I'm not going to be able to get it. Now let's do some heuristics here. The radius, the height, is it has a fuzzy relationship to our width, doesn't it? It looks like another random variable. These guys have about the same width and drastically different heights. And likewise for a couple of these thinner guys. Well, I don't know, but if I'm willing to give up the radius or the square of the radius for another power of height, I'm just doing heuristic analysis. So if I'm willing to give this up for another power of height, well, I would be within a constant of that power of height. I think so. Now it's fuzzy, and so I have yet another, there I go again, yet another function of a random variable, but I could do it. Now, I've said this is a discrete variable again because we're going to maybe do some kind of survey and try to get at it. And it looks like I have some data anomalies here. You can see I did some data conditioning that made a little spike here to the left. That's almost certainly an anomaly. So we have to design this experiment very carefully. But I think I've expressed the weight as a function of 3 random variables. And if I do a little algebra here, let's take this height squared over to the denominator here, and then I've rewritten it left to right. I've got this, all the stochastics, all of the Monte Carlo effects are here. This is governed by some crazy convolution of these random variables. But I've got things that I can measure in the laboratory over here on the right. And at this point, I'm just going to give this Monte Carlo thing a name. I don't know, I'm going to call it body mass index. I'm just going to make something up there so I can get on with my work. But I've got things that I can measure in the laboratory here, and that is a third order effect. It's 1 factor of the weight divided by 2 factors of the height. That's kind of interesting because can you remember the weight divided by height a while ago gave us a little lift, didn't it? And gosh, this is exciting. So now I'm excited. I'm going to go into the laboratory. I'm going to, first of all, prepare an experiment where I can go after these third order features. And here they are. I've got the cube of each, the square of one times the other. I've got the square of one over the other, and I've got one divided by the square of the other. The weight over the height squared, I've just given a name called the body mass index, just made it up. And its reciprocal is here, and they're both statistically significant, as you'll see in a moment. So I'm going to go into the laboratory, and I'm going to prepare my experiment. Here it is. My pre-obese is 1. I've got my body mass index here. Of course, I've got lots of other information, but I'm not going to take that into my model matrix. I don't have to. I just did science. I'm not guessing anymore. I'm not p-hacking anymore. I'm absolutely chasing this hypothesis. So let's do it. Oh, gosh, it's statistically significant with some funny numbers because I didn't scale and center. But the problem is this thing does not work. This decision boundary does not work at all. Look, I'm back to where I started. I can't even get up to 81.4% here. It looks like maybe asymptotically it's going to get there. My true positives fall off. I've got this wonky threshold that's totally unsatisfying. This thing didn't work at all. What's going on? Well, what's going on is that this decision boundary is very difficult. It's the blue guys are in the middle of the black and red guys there. There's 6 things going on. It's kind of flat in 2 space. They're kind of curvilinear anyway. They sort of, they're kind of convex. I don't know, maybe non-convex or something. I mean, I don't even know what's going on there. So I have to do some science. I have to actually stop and go into the laboratory and do some design of experiment. And here's what I have to do. First of all, I have to prepare a series of experiments that will isolate that yellow decision boundary right there. I have to separate the left from the right. And that may take weeks, that may take months, that may take years, that may last a whole career, depending on the difficulty of the problem. And then I'm going to go into the laboratory once I have that done, and I'm going to try to discriminate on the right-hand sliver of the left-hand side. And once I accomplish that, I will have characterized the blue guys. That's what I have to do. So this is a different workflow than p-hacking a machine learning experiment. No number of p-hacks are going to get me to root cause analysis of the data generating function of these physics. So let's get to work. All right, so I'm going to prepare an experiment here. I'm going to mark up my analytic data set here, the GBB, the good, better, best. I'm going to take as my class the pre-obese, the normal, and the underweight, all 3 of those. Let's get our accounting here. I've got 500, 2,800, 4,800 minus a haircut, 47. Here it's 4740. Okay, I buy that. 5 and 6 is 11. Yeah, 4741. So it looks like I marked it up correctly. That's my class, and I'm taking only my body mass index. Well, what happened to the other features? Listen, I don't need them. I've done science. I have a hypothesis. Okay, I don't need to be p-hacking the heck out of this thing with fancy machine learning algorithms. I'm proving a hypothesis and prosecuting a data science experiment, not just machine learning. Well, it's not statistically significant, and that's very upsetting. Remember, I haven't centered and scaled, so these are unsatisfying. But I really wish that would be statistically significant. Why is it not? Well, the answer is the data is dirty. That's a design of experiment issue. And in fact, you'll spend most of your time not running algorithms in data science, but capturing good data. And if you go to any physics lab in any graduate school anywhere in the world at 4 in the morning or 3 in the morning, you will find graduate students hunting for data in their experiment. It is hard work. Well, nevertheless, it's not statistically significant yet. I've got to do some work on the data set, but look at that. It is a perfect predictor, and that's a prediction on the training set, and so it's fair to you to ask what happened to the testing set. I'm out of room on this slide, but I promise you the testing set is also perfectly predicted. The holdback set is likewise perfectly predicted. So we did it. We successfully developed a hypothesis, and we got it very nicely here. I need to clean up the data to get some better statistical significance there. In other words, the standard error is just going to gobble up my prediction. I wouldn't know what to publish here. The answer could be several multiples of my standard error, and I wouldn't even know it at this point. So I'm only beginning on this research program, but I am in the hunt. My physics is supporting very strongly a hypothesis, but I've got to get better data. Fantastic. Let's keep going. Well, so I've got the left half, I've got this boundary drawn, so I've got to take a subset of my data set. So my analytic data set is going to be only the left-hand side now, the pre-obese, normal, and underweight. I've got to scale everything because I'm throwing the right-hand side away, so I've got to do some work here and get that done. And then I'm going to mark up my Y to be only the pre-obese, which is the blue sliver of the left-hand side only. These guys are gone now. The red, green, and blue are out of the research now. And I've got 1,860, and there it is. Looks like I marked it up correctly. Let's do it. Again, it's not scaled and centered. This is unsatisfying. It's not statistically significant. My data is dirty. However, it is a perfect predictor. And so again, I don't know what to publish. My standard error is going to gobble up my estimation, so I have nothing to tell anybody yet. But I'm in the hunt, and again, this is training data, but I promise the testing data, the holdout data also was perfectly predicted. Well, we did it using science, using hypothesis testing. We certainly used some statistics. I suppose you could call it machine learning to help us do our data reduction. But the thing that was key to this result is that I prosecuted this data science research program to isolate the pre-obese data. Now, this could be a hard job. Using as a metaphor the solar spectrum of our sun, what if I was going after these transitions and trying to understand what's going on there? I mean, you're not just going to dive in and do that. You may have to, do various experiments and avail yourself of other published research, and developing your data set is very, very, very expensive. More on that in a moment. But as a metaphor, and I don't know what that is, it's some kind of transition around 6,000 Kelvin. I can tell from the optical color of the spectrum here. But anyway, it could be not only a large research program, but perhaps your entire career, where you're doing dozens and dozens and dozens of experiments and just pushing it forward a piece at a time. Well, let's use a different way of thinking. Remembering our expansion of the radial kernel and powers of our features, let's just take some liberties here and engineer some features. So I've got 1, 2. These are my first, second, and third order features, by the way, that we've built together. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different features. I'm going to try to draw a 14-dimensional hyperplane in 15-dimensional space and see if we can get some good discrimination. I'm going to try to lift the blue guy out of the plane of the other guys and draw a hyperplane between them. Let's see if I can do that. Well, again, I haven't centered and scaled anything. Look at these crazy exponents, so that's unsatisfying. Everything is statistically significant. Now, this is important. How can that be? Remember, I've got the physics worked out. This is the body mass index. I'm sure of it. Okay, the analytical theory here is very strong, but all these other guys are emerging as helping me draw this hyperplane. What does it mean? Well, it turns out it's a perfect predictor almost. I think out of 10,000 training examples, there were a couple of false positives and 3 false negatives. Likewise for the testing set, the holdback set that I haven't shown you. And again, I apologize, I'm out of room on these slides. So what's going on? Well, the difference is we're not doing science here. We're doing machine learning. And it's absolutely essential we understand those are two different things. So I did successfully pick the blue guys, the pre-obese, out of the rest of the data set. I've done that, and I can predict on it, and I can take action on that. But I'm no closer to understanding the root cause than I was before I did my analytical theory and identified this function of 3 random variables, which I've called the body mass index. So that shows the difference between a data science research program and some machine learning. Now, this is actually important news. As we sit here Sunday the 17th of February, just a day before yesterday, Friday, the BBC reported an article, and others have picked it up, on the American Association for the Advancement of Science conference, where Genevera Allen here, which I've showed with her, who took her PhD at Stanford with her dissertation advisor, Rob Tebshirani, and you know Tebshirani from the lasso technique. His PhD advisor at Stanford was Bradley Efron, who's emeritus now, but he invented bootstrapping, which many machine learners use. So this academic family is very deep into genomics research, bioinformatics, pharmacological chemical research, support with data engineering. And Genevera gave a speech at the AAAS conference, and she said, listen, there's lots of falsifiable research being published, and this will not do. And there's a reason for it. Data sets for certain problems, astrophysics, genomics, and so forth, are very expensive. And so it's compelling to take someone else's data set and apply machine learning techniques to it and try to reach some new conclusions. The problem is machine learning, as I've just showed you, has no insight whatsoever into root cause analysis. Machine learning is not science. It is not. It is not science. It cannot help you, per se, prosecute a data science research program. What it does very capably is find patterns in the data set. And what Genevera is saying is, listen, those patterns are not the physical effects. They aren't the cause among the correlations. Those patterns are just signals in the noise, and they are idiosyncratic to the data set itself. And so if you have a new data set, you'll have new machine learning patterns and new machine learning conclusions if you're foolish enough to make a conclusion on a machine learning result. And indeed, that's what's happening. So, and in fact, once these expensive data sets are superseded by other expensive data sets, most of that research is falsified and is considered invalid. It always was invalid. It shouldn't have been in the journal in the first place. In fact, she shows in her field that 85% of biomedical research is exactly wrong. And again, these are in peer-reviewed journals. So this is a crisis of academics. This has to get fixed. There's probably no better team to fix it than these three. The Stanford Statistics Department has been out in front ever since Miller founded the thing at Stanford back in his day. So this will get fixed. It's getting called out, but it's definitely in the news, and it's definitely germane to my remarks today. If we take one thing away from this talk, machine learning is not science. It can support science if you have a good design of experiment and a good research program to isolate a physical effect. Remember, I showed you that the data was dirty, and so I do not have publishable results yet. I've got to clean up the data so I can get statistical significance from my predictors, and I have to completely check my analytical theory and have other peer review efforts to validate my own analytical theory. Lots to do to marry machine learning with science. So remember, using this spectrum as a metaphor, I showed you that we can kind of chop away at it. We can do a series of experiments in our research program to isolate one series of the data set. I'm using the spectrum as a metaphor, and then another set of experiments to isolate this effect on which I can make a scientific conclusion. That is important. And remember, again, as a metaphor, using the solar spectrum, I showed that maybe these effects are very hard to get at and could comprise not only weeks and months, but perhaps even an entire career to isolate perhaps certain transitions in a spectrum. Machine learning does nothing like that. Nothing like that at all. It cannot find root cause in the correlations. It doesn't even try. But what it does very, very capably is show us a way forward to make a decision on this data, and that is a very different thing. Well, those are my remarks today. I'm at your service for questions, and I will turn it back to the moderator, and I'm very grateful for your time. Thank you.